In this module 4.2, we'll work out some examples of normal distribution using the standard normal table. So in the first example, we'll consider a part assembly that's retained on a shaft by 5 bolts, and they have to be tightened to a specification that's given here, torque of 14 plus or minus 5 Newton meter. And then 20 assemblies were checked for bolt torque. So 20 assemblies with 5 bolts each, total of 100 bolts. They had a mean of 37 Newton meter and a standard deviation of 1.5 Newton meter. So assuming that the torques are normally distributed, estimate the proportion below 35 Newton meter. In other words, the torques are all normally distributed for these 100 bolts. And so we're asked to estimate the population below which we would have failure, because we would not accept any torque below 35 Newton meters. So this is my window here, right? So we want to know the population below 35 Newton meter. So the way we would do this is we will first estimate my standard normal. We would first calculate my standard normal variable, z corresponding to 35. And that would give me, that's how I would estimate the population below torque of 35 Newton meter. So that's, and the mean value is 37. And therefore, the mean value is 37, standard deviation is 1.5. That gives me a z value of negative 1.33. So now I need to calculate the CDF corresponding to minus 1.33, which we know is 1 minus the CDF corresponding to plus 1.33. And I can estimate this value from the table, and that value is 0.90824. We'll see how that is to be estimated. So let's go back to the table from the previous module. So I need to find the value corresponding to 1.33, and I actually need to find the value corresponding to 1.3333. But the table is only accurate to second decimal place, so it only has value up to 1.33, and that is 0.90824 from the table. So that's how I got the value in my example of 0.90824. And this value would be different from what you would estimate from a computer, because the computer will be more accurate. So this value is only accurate to the second decimal place, 1.33, whereas if you were to use a computer, you can estimate up to the fourth decimal place, and that value would be slightly different from what you have here. And the probability then turns out to be 0.09176, which means 9.1% of your assemblies would fail because they would have a torque below 35 Newton meters. Let's go on to the second example, which is our bearing example that we did previously for expectation and variance. Now we'll do it for a normal distribution. Let's assume that shaft is to be assembled into a bearing, and given that the diameter of the bearing is normally distributed with a mean value of 1.5, standard deviation of 0.04, and the shaft is also normally distributed. Shaft dimension is also normally distributed with a mean value of 1.48 and standard deviation of 0.03. And what is the fraction of assemblies would fail due to interference? As before, we define x as the diameter of the bearing minus the diameter of the shaft. The mean value, as before, is the difference in mean values, which is 0.02. And standard deviation, as before, we can estimate the variance, as before, is sum of the variance of the bearing and the shaft, which is 0.0025. Now what we seek is the probability that x would be less than 0, which is interference. So probability that x is less than 0 is probability that z is less than 0 minus 0.02 divided by 0.05, 0.05 being the square root of 0.0025. So that in turn requires us to estimate phi corresponding to negative 0.4, That's 1 minus the phi corresponding to 0.4, which is 0.3446, so 34% possibility of interference. So it's a slightly more involved problem. So we first needed to estimate the mean value and the standard deviation for the variable x, and then use that to estimate our probability. Let's go on to the last example. So a manufacturer targets 30 minutes for assembly and testing. Together 30 minutes, but it takes 12 minutes on an average to assemble with a standard deviation of 3 minutes. And testing takes 10 minutes on average with a standard deviation of 2 minutes. So if the company makes 1,000 parts a month, roughly how many parts exceed the target time of 30 minutes is the question. So we might do this to estimate whether 30 minutes is sufficient. Okay. So how would we go about solving this problem? So we're given that the total time is sum of time to assemble and time to test. And then we need to estimate the time that from the statistics of these two, the probability that the total time will exceed 30 minutes. Okay, so let's do this. This is example 3. Let's say assembly time is x. Let's call that random variable x. And testing time, let's denote that with a random variable y. Total time, then let's call that total time as some z. Z is, maybe we'll just call it t. T is equal to x plus y. Okay, total time is x plus y. So what we seek is probability that t would exceed 30 minutes. First, we need to find the mean value of t. So t bar we know is x bar plus y bar, which is equal to 12 minutes for assembly, mean value of 10 minutes for testing, which is 22 minutes. And we also need the standard deviation of t, and that is standard deviation of x, variance of x, plus variance of y. And we are told that the variance of x is 3, so this is 3 squared plus 2 squared. So that gives us the standard deviation of the total time to be equal to 3.0605 minutes. All right, so what we need is probability that t is greater than 30 minutes. So now we will use the standard normal variable. The standard normal variable corresponding to 30 minutes is 30 minus 22 divided by 3.605. That's 2.219. Okay, that's my z value corresponding to 30 minutes. And remember, phi of z represents the probability that t would be less than or equal to 30 minutes, right? And therefore, this is equal to 1 minus the probability that t would exceed 30 minutes. Okay, so what we then seek is probability that t would be greater than 30 minutes, and that will be equal to 1 minus phi of z. Okay, and phi of z corresponding to 2.219 is 0.9867. So this is 1 minus 0.9867, which is equal to 0.0132. So the probability that time would be greater than 30 minutes is 0.0132. Therefore, for 1,000 parts, what you would get would be 1,000 times 0.0132, which is equal to 13.2 parts would take longer than 30 minutes total. Okay, with that, we are done with the examples of normal distribution. With that, we are done with this module 4.2, examples of normal distribution.